Mastering fuzzy logic control. Fuzzy logic control mechanisms exploit uncertainty and ambiguity to yield astonishingly accurate results. What mechanisms does fuzzy logic control employ to effectively address and mitigate the impact of uncertainty and ambiguity that arise from inherent inaccuracies and vagueness in process data? Fuzzy logic control employs several mechanisms to effectively address and mitigate the impact of uncertainty and ambiguity that arise from inherent inaccuracies and vagueness in process data. Firstly, fuzzy logic control uses fuzzy sets, which are sets with fuzzy boundaries, to represent linguistic variables and handle the vagueness and imprecision in process data. Fuzzy sets allow for the representation of partial membership, which enables the system to capture the ambiguities and uncertainties present in the data. For instance, in a temperature control system, the concept of high temperature can be represented as a fuzzy set, allowing for a more nuanced and flexible representation of the temperature range. Secondly, fuzzy logic control uses membership functions to quantify the degree of membership of an element in a fuzzy set. Membership functions map the input data to a membership value between 0 and 1, indicating the degree to which the input belongs to the fuzzy set. This allows the system to capture the uncertainty and ambiguity in the data, as the membership value can be interpreted as a degree of truth or probability. For example, in a pressure control system, the membership function can be used to represent the degree to which the pressure is high or low. Thirdly, fuzzy logic control uses fuzzy rules, which are if-then statements that relate the input variables to the output variables. Fuzzy rules are used to encode the expert knowledge and experience of the system designer, and they provide a framework for reasoning about the uncertainty and ambiguity in the process data. Fuzzy rules can be combined using various logic operators, such as AND, OR, and NOT, to create complex rules that capture the relationships between the input and output variables. Fourthly, fuzzy logic control employs defuzzification methods to convert the fuzzy output into a crisp value. Defuzzification methods, such as the center of gravity method or the mean of maximum method, are used to calculate the output value based on the fuzzy output. This step is critical in fuzzy logic control, as it enables the system to produce a clear and actionable output despite the uncertainty and ambiguity in the process data. Fifthly, fuzzy logic control uses feedback mechanisms to adjust the control signal based on the system's response to the previous control signal. Feedback mechanisms, such as the proportional integral derivative (PID) controller, are used to fine-tune the control signal and ensure that the system converges to the desired state despite the uncertainty and ambiguity in the process data. Lastly, fuzzy logic control can be combined with other control techniques, such as model predictive control (MPC) or adaptive control, to create a hybrid control system that leverages the strengths of each approach. This hybrid approach enables the system to handle complex and nonlinear relationships between the input and output variables, as well as to adapt to changes in the process dynamics and uncertainty. In summary, fuzzy logic control employs a range of mechanisms to effectively address and mitigate the impact of uncertainty and ambiguity that arise from inherent inaccuracies and vagueness in process data. By using fuzzy sets, membership functions, fuzzy rules, defuzzification methods, feedback mechanisms, and hybrid control approaches, fuzzy logic control provides a robust and effective means of controlling complex systems despite the uncertainty and ambiguity present in the process data.